Hi, my name is Zachary Lyons, and today I'll be presenting the Physics 2212 Lab Number 1 Charge Tape Lab at Georgia Tech. The goals of this lab were to prepare two pieces of charge tape and observe the interactions between the tapes and other objects. We were then going to find the excess charge on one piece of the charge tape and then simulate the interactions using a computational model in VPython. The findings of this lab were that the tape had a net positive charge with a value of 1.42 times 10 to the negative 8 coulombs. The tape was found to be deficient of 8.875 times 10 to the 10 electrons, giving it its positive charge. Some key concepts for this lab are Newton's second law and the gravitational force. Newton's second law states that the net force on an object is equivalent to the change in momentum over time. And the gravitational force is shown by this equation here, and it points in the negative y direction, with g being equal to 9.8 meters per second squared. Another key concept for this lab is Coulomb's law, which is shown here to be the Coulomb's constant times the two charges divided by the magnitude of the distance squared, and it points in the r hat direction, which points from the source to the point of observation. This is how we find the electric force on the suspended tape, and the Coulomb's constant K has a value of 9 times 10 to the 9 Newton meters squared per Coulomb squared. The magnitude of the electric force does not depend on r hat, and it does not depend on the sign of the charges. Some assumptions for this lab were that the tape acts as a point charge and that the point charge is located at the center of the tape. The tapes can be modeled as a point charge in the computational model, and we assume that air resistance is ignored. We also made the assumption that both tapes have the same amount of charge. Using the procedure shown, we were able to suspend a tape and then introduce the charge tape below it by a specified separation distance d. We placed a base tape on a table and then ripped another tape off. This is what rips off some of the electrons from the tape and gives it its positive charge. And following the procedure, we modeled the interactions from the scenario of the suspended tape in the computational model. Based on putting the two tapes together after they've been charged, we found that they repelled each other, which means that they have the same charge. And then based on the interaction between the U-tape and the hand and the U-tape and negatively charged pen, we found that they attracted. And since we know that the pen is negatively charged, the tape must be positively charged. And since the two tapes repelled each other, they can be assumed to have the same sign of their charge. The suspended tape and the charged tapes were held by a separation distance of 0.025 meters, which is approximately 1 inch. The system of the computational model is the suspended tape. That's our system. And then the surroundings is the charged tape being held underneath. The only forces acting on the system, which is the suspended tape, is the electrical force pointing upwards from the tape and the force due to gravity pointing downwards on the tape. Since the suspended tape is not moving, we assume that the net force on the system is 0. Thus, it allows us to create our computational model. The data and calculations for the force of gravity is shown here. Since the mass of the tape was found to be about 2.88 times 10 to the negative 4 kilograms, we were able to find the force of gravity. And since we know that the electrical force is equivalent to the force of gravity, we're able to substitute that into Coulomb's law. And using the following equations, we're able to find the charge of the tape, which is 1.42 times 10 to the negative 8 coulombs. In order to find the number of deficient electrons and the ratio of deficient electrons to the number of atoms in the tape, we found the area of the tape, and we found that the area of we looked up the area of an atom, which is 1 times 10 to the negative 20 meters squared, and then dividing the area of tape by an area of atom, we were able to find the number of atoms. Then by finding the charge of an electron, we divided the charge of the tape to find the number of electrons, which is 8.875 times 10 to the 10 electrons, and we were able to find the ratio shown below. The constants are represented in the code here, and the forces acting on the object are translated into code here. The equations for the forces are shown here, and they're translated into the glow script shown below. Here is a visualization code here that creates the point charges and shows the arrows of the forces acting on them, and the text for the quantities are shown here. These are the results. The numbers match our calculations, and a visualization model is shown. So, based on the lab, we found that the tape is positively charged, which means that there is an electron deficiency. The tape is floating, which means it's in static equilibrium, and the force of gravity must be equal to the electric force. Some sources of error may be inaccurate measurements of the tape dimensions, as well as separation distance, and some rounding error. And the held tape may not have been held exactly parallel with the other tape, which may change the magnitude of the distance. So what if the electrons had positive charge and the protons had negative charge? Would the observations change? Yes. The E fields for the objects would change if the signs were switched, and the positively charged tape would be negatively charged, and the E field direction would be switched. The observations made would not change since they would still repel each other, and the plastic pen would still be attracted to the tape. Why is it important to touch the tapes as little as possible? Well, charge can be transferred from the hand to the tape. Thus, there could be a change in charge, and it would be overall less positively charged. Thank you.